In this video, I'll run through complete solutions to the first 4 calculator active multiple choice problems from the released 2012 AP Calculus AB exam. These are calculator active, so make sure you have your calculator beside you so you can follow along. Let's dive in. So in this first problem, I know I just said these were calculator active problems, but there are no numbers in sight. We've just got a graph and a question, so we actually won't need our calculator for this one, as is often the case on these calculator active sections. So we've got this graph of f, and we want to find the x value at which f prime is both positive and increasing. Okay, so we've got 2 facts we need to use here. So the fact that f prime is positive, that means that f is increasing. That's what it means for a function's derivative to be positive. So I can rule out several of these points already, right? It can't be at x equals a because the function is decreasing. Similarly, at x equals d, the function is decreasing. And at point x equals b, okay, f prime doesn't exist because we have that sharp turn in the graph. So if the function doesn't, if f prime doesn't exist, it certainly can't be positive. Okay. So we now have these 2 candidates left, x equals c and x equals d. To break that tie, we're going to have to use the second fact, namely that f prime is supposed to be increasing. Well, if we remember what that tells us about the function f prime being increasing means that f is concave up, right? If f prime is increasing, the second derivative f double prime will be positive. That's another way that you can recognize concavity, okay? So if we look at these 2 points, we can see at x equals c, nope, the graph is concave down, so it must be the case that x equals e is the point we are looking for. And you can see, indeed, as we move along the graph here, the graph is getting steeper and steeper. So the tangents are getting more and more steep. Their slopes are getting more and more positive. And so that must mean that f prime, the measure of the slopes, is increasing. So the answer here is E. On to the next question, multiple choice number 77. This question is all about applying the intermediate value theorem. So we're given a setup that allows us to apply the intermediate value theorem, and we need to figure out the correct conclusion that we're able to draw. Now, in an intermediate value theorem problem, what I like to do is draw a quick sketch of the information that I have been given. Okay, so I'm told this function is defined on the closed interval 2 up to 4, and it's a continuous function, and at x equals 2, my function takes the value 10, and at x equals 4, my function takes the value 20. Okay. Now, what does the intermediate value theorem tell me? It tells me that when I start at this value of 10, I need to climb up to the value at the other end of the interval, okay, namely at x equals 4. I know I'm spitting out this output of 20. Because my function is continuous, the intermediate value theorem says I need to hit all of the values in between that are intermediate to y equals 10 and y equals 20. So in particular, if I scan down my answer choices, do I see any numbers that are between 10 and 20? Well, I see 13 and I see 15. And this is where I start to experiment maybe. Okay, maybe you've already spotted the correct answer. If you have, that's great. You've probably been practicing your intermediate value theorem problems. But here, maybe I'm not sure. So this is where I start experimenting with my little sketch that I've got. So let's look at B. Okay, so B says that f of 3 is supposed to be 15. Is that the case? Does that need to be true about this function because of the intermediate value theorem? Well, no, because if that were the case, Well, there's a couple of things I'll say. First of all, that is not what the conclusion of the intermediate value theorem looks like. It doesn't tell you anything for sure, okay? It just tells you that something has to happen. It doesn't tell you what that thing that's going to happen is concretely. So the fact B is trying to say f of 3 is concretely equal to something, that is setting off an alarm bell in my head, okay? So really, in this sketch, I'm saying, is there a way for me to connect the point 210 to the point 420 with a continuous function graph without passing through the point 315? I mean, yes, for sure, right? I can do lots of interesting things to avoid that particular value at x equals 3. So I'm pretty sure B is not going to be the case. But let's think about A then, because 13 also lies between those values, y equals 10 and y equals 20. And now the game is a lot more difficult, right? Because it's saying there has to be at least one solution between x equals 2 and x equals 4 that gives me that output of 13. Well, I can try as much as I want, but if I start at the point 2, 10, and I'm trying to sort of join the dots, I know I eventually need to hit that point 420. If my graph has to be continuous, I'm not able to get around the fact I've got to cross over that line y equals 13 sometime, at least once, maybe more than once. But as soon as I've crossed over it at least once, that gives me a solution to f of x equals 13. And this is exactly what the intermediate value theorem tells us has to be the case. So if we're confident in that, we can move on to the next problem if we're under time pressure on the exam, which we will be. But since I have you here, let's rule out the other cases too, because if we weren't sure what the correct answer was, we could always do a process of elimination to try and figure out the right answer. So if I make a copy of this little sketch and tidy it up. Okay, what do I want to leave? I'll certainly leave my endpoints. There we go. Okay. So C is saying that the function f has to attain some maximum value between 2 and 4, that open interval. Well, that doesn't need to be the case. It's also not what the intermediate value theorem says, but let me show you why that needn't be the case. If I do something like this, and then go really steep up towards that point at 420, well, that is making the function take its maximum value at x equals 4. Okay, the maximum value of this function that I've drawn is 20. But remember, it's the open interval to 4 in the answer choice. So really, I have this, I'm looking at what's happening. I've got this open endpoint here. And if I zoom in a load, okay, you can see as I'm getting closer and closer to x equals 4, the function just keeps getting larger and larger. Okay, because I'm not allowed to ever reach x equals 4, I never attain that maximum value. And so there is no maximum value attained on the open interval. So that can't be the answer choice. Part D is sneaky because it looks, or answer D rather, is sneaky because it looks like the same sort of format as answer A. But this is trying to apply the mean value theorem. Okay, the mean value theorem is what talks about f prime, the derivative of the function. So a couple of reasons this can't be right. First of all, it's trying to apply the mean value theorem, not the intermediate value theorem. And also, we actually can't apply the mean value theorem here because we don't have the conditions satisfied. The mean value theorem needs to talk about the function being differentiable, having a derivative, not just continuous. We don't have differentiability as a condition here. So I can actually cook up a counterexample. So this is trying to say there has to be a point between x equals 2 and 4 where the derivative, the slope of the tangent is 5. Okay. Well, I could do something like go really, really steeply up like that. Maybe the slope is, I don't know, 10. And then I can sort of slam on the brakes and just go horizontally over there. So by having that sharp turn, my function is not differentiable. So I can't apply the mean value theorem, and I say, oh, actually, D doesn't need to happen either for this continuous function. Finally, in part E, it's trying to say, or answer choice E is trying to say, is the derivative, does it always have to be positive for every x? Well, no, there are lots of things I could do where the derivative would be negative. Right, as soon as the function starts decreasing, my graph slopes downwards. F prime is going to be negative, not positive. So I've cooked up a counterexample there. Okay, next multiple choice problem. This is number 78, and this is actually the only problem in today's video where you will need your calculator. So if what I run through on the calculator is a bit mysterious to you, that's okay. I'd encourage you to check out my calculator skills video. I'll put a link in the description down below that runs through the 4 calculator skills that you need to know for the AP Calculus exam that come up every single year, explain them from scratch. So if this seems a bit, wait, what? Take a look at that video, come back here, it'll make more sense, I promise. So here we're looking for a point between 0 and 1 where the graph of this function crosses the x-axis, and we want to know what the slope of the graph is at that point. So what's the slope of the tangent to this graph at that point? And we have some choices here. Okay, well, let's start graphing. So the first thing we need to do is figure out this x-intercept between 0 and 1. So let me pull up my calculator app. You can follow along on your physical one at home. So let's enter in our function. So it is e to the power of tangent x subtract 2. Okay. Now, before we go any further, let's make sure that your calculator is in radians mode, okay? Because we're about to start doing some calculations with a trig function, okay? I know you think your calculator is always in radians mode at this stage in calculus, but you might have done some weird memory reset. You might have an arch rival in class who has secretly changed your calculator into degrees to mess you up. So it's always worth checking, does it say radians at the top? When I quit out of this, oops, I can see I am indeed in radians. Great. Okay, so if I go and plot my graph, like, okay, great. That's kind of a bit busy. I know I want to be looking at x from 0 up to 1, so I may as well show off that I can change the window here, the window setting. So let's make my x min 0 and my x max 1. If I now graph, there's that one intercept, that one x-intercept that I'm interested in. So I'm going to hit second trace to calculate the 0. So menu item number 2 here. As is always the case, I need to sandwich the x-intercept that I'm interested in. So I want to know the left bound. I need to navigate over and sandwich it on the right. I'll hit enter. On your physical calculator, you'll then hit enter one more time to get your guess of what the intercept is. And here you can see x equals 0.606 is my x-intercept between 0 and 1. And that's one of our answer choices. But we're not going to fall for that, are we? Right? This was an intermediate step. This is just the x-intercept. I want to know something about the graph at this x value. Okay, it's kind of sneaky. They put it on there as an answer choice. I'm sure some people will fall for that, but we are not going to. So we need to figure out f prime of x, dy by dx, evaluated at this x value. Okay, let's clear out. Oops. So the first thing I'm going to do, because I don't want to make a mistake typing in values, and I want to use the full value that it has given me, I'm going to store that x value. So it's currently remembering it as x, right? I'm just going to store it. So hit x, I'll then hit this store button down at the bottom, and I'll store it in my favorite variable, a. I'll hit alpha math to get a. And now I'm just using the letter a to remember that value, because now I can call it when I set up my derivative calculation. Okay. So I'm going to hit Math, then entry 8 for n deriv. You'll have to select the variable you want to use on your physical calculator. I think you may as well hit X. Now you certainly could enter e to the tan x minus 2 again here, but you can also use your y variable. Remember, in our y equals menu, we entered that as y1. Okay, see, it's right there. So what I can do is I can hit alpha trace to bring up my y variable menu and just enter y1 there. If you don't like this, you can by all means just enter e to the tan x, subtract 2 again. But that can save some time, make you less likely to make a mistake. So it can be a helpful little tip there. Now again, you could type in 0.60611 here, but because I stored it as a, I'm just going to call that variable now. And when I hit enter, I get my correct value here. So that is 2.961 to 3 decimal places. Let's clear away my calculator. Oops. Great. And is that one of my answer choices? It is indeed. Thank goodness. So let's look at this final fourth multiple choice problem for today's video. It is asking us to figure out an expression that gives us the average velocity of this particle that's moving along the x-axis from t equals 0 up to 8. So average velocity, that's asking for the average value of the velocity function. So if this was in general, if we wanted the average value of an integrable function on the interval a up to b, that's a formula for us to remember. So it is, we take the integral from a up to b of our function, and then we divide it by the length of the interval. So 1 over b minus a. So here we have a few specifics, right? What we're really looking at is v of t on the interval up to 0, 8. So if I substitute into my formula, I'm going to get the integral from 0 up to 8 of v of t. Okay, that's my variable we're using for this time-based problem. And then I need to do the length of the interval. So that's 1 over 8 minus 0. That's just 1 over 8. Oh, is this one of our answer choices? Well, yes, it's answer choice B. So that is the correct answer. Let's move on. But since I have you here, let's do a process of elimination. If we weren't sure what the correct answer was, we could score out some of these and hone in on the correct answer more closely. Answer choice A, that is a formula that we know. That is calculating the average rate of change, not of the velocity, but of acceleration, right? It's a of 8 minus a of 0. So not only is that the wrong quantity, it's the average rate of change, not the average value. It's the wrong function entirely. So we can be pretty sure that is not the correct answer. Choice C looks tempting. It's very similar to our correct answer. But those absolute value bars are super important. Okay, that converts our velocity, which has direction, into speed, which does not have direction. So this is giving us a calculation of the average speed of the function over this time interval, but that's not what we were asked for. Okay. Part D also, answer choice D also looks similar to the correct answer, but that 8 is wrong. Okay, I think they just put a 2 there because they wanted to have a 2 in the next answer choice. I don't know, but it is not correct. It does not match up with what we were wanting. Answer choice E, this is kind of cute. This is taking the average of the two values, v of 0 and v of 8, right? It's adding them, dividing by 2. That's a classic average, okay? But we know at this point that velocities of particles, objects in the world can be very, very complicated and interesting. So it's probably not going to fully capture the average value of the function just by looking at the endpoints and taking the average there. This would be true in the case that the acceleration is constant. So your graph of velocity is just a straight line. If you think about why this would give you that midline halfway up between the starting velocity and the ending velocity, but in general, this is just not going to give us the right answer. So there you have it. That's a quick run through of the first 4 calculator active multiple choice problems from the 2012 exam. If you need to brush up on your calculator skills, as I said during that third problem, I'll put a link to my calculator skills video down below. If you want to practice more multiple choice problems from this exam in order, I'll put a link to the full playlist here. Apart from that, I just look forward to seeing you in the next video. Bye.